Traditionally, pilots perform pre-flight cockpit system checks through paper checklists or memorization. Without any guidance, this can lead to cognitive overload or underload and an increased potential for mistakes. This research aims to test the benefits of AdaptiveCoPilot, an adaptive multimodal feedback system implemented in a virtual reality cockpit that provides real-time neuroadaptive guidance based on pilots' cognitive states and performance. We first conduct a formative study, which consists of aviation expert interviews to explore the following research questions. Research. Question 1. How do varying cognitive states impact a pilot's ability to process and comprehend information during flight operations? Research question 2. In what ways can a guidance system dynamically adjust to enhance performance and safety? Research question 3. How do different modalities, visual, auditory, text, affect cognitive states, and how can adaptive modality switching optimize task execution for pilots? Our formative study was conducted on 3 experts from the aviation industry. Based on the findings, we summarize 3 design requirements for developing an adaptive, multimodal feedback system. The system should help avoid cognitive overload and information redundancy. The system should dynamically adapt the feedback modalities and information density based on the task complexity and the pilot's cognitive state. The system should proactively correct the errors through multimodal feedback. Based on these design requirements, we developed AdaptiveCoPilot to provide dynamic, adaptive guidance through text, audio, and interactive cues based on real-time assessments of the pilot's cognitive state and performance. To evaluate the effectiveness of AdaptiveCoPilot, we conducted a case study involving 8 licensed pilots with varying levels of expertise. Runs were split into one of 3 conditions: baseline, random guidance presentation, and adaptive guidance. During each run, pilots performed a 3-procedure subset of a real Black Hawk pre-flight checklist. This graph looks at the optimal workload rate across each procedure and condition. For all procedures, we see a higher level of optimal working memory states for the adaptive condition. For perception, we see a benefit over baseline for both guidance conditions. Within guidance conditions, we see that adaptive performs better during procedures with inputs, and random performs better for procedures with value checks. This figure shows the completion time in seconds between procedures and conditions. We can see a general trend across all procedures that the adaptive condition has a lower completion time. This figure shows the error rate between procedures and conditions. We can see that baseline error rate is slightly lower than both guidance conditions. We theorize that this might be due to a sense of complacency that the user may feel when the guidance is on. We summarize a set of strategies for designing and studying future neuroadapted flight guidance systems based on our initial findings in the formative study and our case studies, qualitative and quantitative results. Adaptations should be based on task complexity and cognitive state, minimize guidance overload and information redundancy, enhance error detection and correction mechanisms, tailor adaptivity to expert and novice preferences, maintain trust with the pilot, and maintain pilot autonomy. In conclusion, we are excited to present AdaptiveCoPilot, a NeuroAdaptive LLM Cockpit guidance system designed and tested on aviation experts.